Hello everyone. In this video, we shall talk about basic concepts, examples, and applications from linear programming. So what is linear programming? It is a mathematical technique for maximizing or minimizing a linear functions of several variables such as revenue, profit, and cost. It is a subfield of optimization theory and is significant in decision sciences. Linear programming can be applied in diet problems where one would want to know the quantity of food intake to satisfy nutritional requirements, such as minimizing calories and maximizing proteins and vitamins. It can also be applied in investment portfolio problems where one would determine the amount to be invested, say in stocks, bonds, and mutual funds, to minimize risk of losing money and to maximize investment returns. It also involves flight scheduling problems where there are limitations in pilot flying hours and time constraints, and also minimize cost of crew overnight accommodation, and etc. Moreover, it also involves transportation problems where the goal is to minimize the cost of transporting goods from one location to another. To fully understand the basics of linear programming, we enumerate and briefly describe its elements. First, the decision variables. These represent the unknown decisions to be made. Most of the time, these variables pertain to product quantities to be produced over a period of time. We normally use x1 up to xn, but since this video covers only the two variable LP problems, then we shall use only x and y. The next element would be the objective function. This is the goal of the problem. The goal is to either minimize or maximize a certain function. The objective function is represented by an equation. Here are some possible objectives. Maximize profit from selling products, minimize cost of materials, minimize employee overtime, maximize the use of resources or manufacturing materials, minimize labor turnover, and minimize machine downtime. The last element would be the constraints. Constraints represent limitation in resources and requirement values for the decision variables. Constraints are combined to form a system of linear inequalities. There are two types of constraints, the resource and the non-negativity constraints. The resource constraints can be one of the following: limitations in raw materials or ingredients. It could be monetary limits, time restrictions, availability of personnel, presence of ability or skills, and could be space capacity. The non-negativity constraints are constraints that assures non-negative values for the decision variables. Since most of the time, decision variables represent production of items, these values should be non-negative. Now let us have a simple example of a linear programming problem. A company produces two types of tables, T1 and T2. It takes 2 hours to produce the parts of one unit of T1, 1 hour to assemble, and 2 hours to polish. It takes 4 hours to produce the parts of one unit of T2, 2.5 hours to assemble, and 1.5 hours to polish. Per month, 7,000 hours are available for producing the parts, 4,000 hours for assembling the parts, and 5,500 hours for polishing the tables. The profit per unit of T1 is $90 and per unit of T2 is $110. How many of each type of tables should be produced in order to maximize the total monthly profit? To solve the problem, we first formulate the linear programming problem. We identify the decision variables. Since the company is selling two types of tables, X would be quantity for table T1 and Y would be the quantity for table T2. Next, we formulate the objective function. Since the profit for table T1 is $90 and $110 for T2, the objective is to maximize the total monthly profit, which we will represent by Z. The total monthly profit is computed using the formula 90 times X plus 110 times Y. Next, we set up the constraints, specifically the resource constraints. In this problem, the resource constraints are limitations in producing, assembling, and polishing the tables. Now, table T1 needs 2 hours of production, 1 hour of assembly, and 2 hours of polishing. Table T2 needs 4 hours of producing, 2.5 hours for assembly, and 1.5 hours for polishing. Now, every month, there are 7,000 hours available for production, 4,000 hours available for assembly, and 5,500 hours available for polishing. Now, in this case, the total production time whenever the company produces X units of T1 and Y units of T2 would be 2 times X plus 4 times Y. And this should be less than or equal to 7,000 hours because it is the limitation for production. Now, for assembly, the total assembly time will be 1 times X plus 2.5 times Y, which is less than or equal to the limit of 4,000 hours. While for the polishing, the total polishing time is 2 times X plus 1.5 times Y, which is less than or equal to 5,500. Now, the non-negativity constraints would be X and Y are both greater than or equal to 0. This is the formulated linear programming problem. To solve the problem, we need to solve the system of inequalities, we graph them, and determine the feasible region. The feasible region consists of all points that satisfy all the constraints. Then, we shall use the corner point principle, and it states that the solution of the LP problem is among the corner points of the feasible region. In the given graph, the white region represents the feasible region. The coordinates of the corner points are also shown on the graph. There are 5 corner points. To determine the solution of the problem, we substitute the coordinates of each corner point to the objective function to determine the possible values of z. The possible values of z are as follows: 176,000, 245,000, 273,000, 247,500, and 0. We see that the company should produce 2,300 units of T1 and 600 units of T2, and this will give the company a maximum profit of $273,000. Here is another simple example. The liquid portion of a diet is to provide at least 300 calories, at least 36 units of vitamin A, and at least 90 units of vitamin C daily. A cup of dietary drink X provides 60 calories, 12 units of vitamin A, and 10 units of vitamin C. A cup of dietary drink Y provides 60 calories, 6 units of vitamin A, and 30 units of vitamin C. Now suppose that dietary drink X costs 12 pesos per cup and drink Y costs 15 pesos per cup. How many cups of each drink should be consumed each day to minimize the cost and still meet the stated daily requirements? Again, to solve the problem, let us formulate the linear programming problem. Let us let X be the number of cups for drink X and Y be the number of cups for drink Y. Now, for the objective, we minimize the total cost. And this total cost is represented by Z, and it is computed using the formula 12 pesos times X plus 15 pesos times Y. For the constraints, it consists of the nutritional requirements for calories, vitamin A, and vitamin C. Now, for the calories, there should be at least 300 calories, at least 36 units of vitamin A, and at least 90 units of vitamin C. Now, drink X provides 60 calories, 12 units of vitamin A, and 10 units of vitamin C, while drink Y provides 60 calories, 6 units of vitamin A, and 30 units of vitamin C. To create the constraints, then the total number of calories would be 60 times X plus 60 times Y, and it should be at least 300, which means it should be greater than or equal to 300. For vitamin A, the total number of units will be 12 times X plus 6 times Y, which is at least 36 units. And for vitamin C, the total would be 10 times X plus 30 times Y, which is at least 90. And then we have the non-negativity constraints, which states that X and Y are both greater than or equal to 0. Now, this is the formulated linear programming problem. To solve this, we need to graph each of the inequalities and determine the feasible region and the corner points. In the given graph, we see that the yellow region represents the feasible region and it contains 4 corner points, namely 0, 6, 1, 4, 3, 2, and 9, 0. Substituting the coordinates of these corner points into the objective C equals 12 times x plus 15 times y, we get C equals 90 for 0, 6, 72 for 1, 4, 66 for 3, 2, and 108 for 9, 0. Since the objective is to minimize the total cost, then our minimum total cost is 66 pesos, which corresponds to 3 cups of drink X and 2 cups of drink Y. And this solves our example. Thank you for listening in my video, and please don't forget to subscribe on my channel. Thank you.